perfect time to visit that place. You'll see very serene view of field and mustard flowering. Anyway, so welcome back for the fourth day of this particular GIAN program, and again we have our guest faculty Dr. Garfred with us, and today's session, first session, will be on application to biofuel. So directly related session, especially for the students working on the biofuels. And I request all of you to listen carefully, as you will be having one examination also tomorrow. It will be a multiple choice based examination, and grades will be given, and maybe it will be transferred to your academic bank of credit scores also. So seriously listen to the talks whatever we are organizing, and then only you will be able to perform good in the tomorrow's quiz. So I will invite the guest faculty today, Dr. Garfred, please. Yeah.
Okay, good morning, everybody. The question yesterday arose, what is more difficult, to get up on a hill to see a temple or to make a life cycle assessment? So what do you think? Anyway, it was a very nice excursion yesterday. And as we already mentioned, there will be some homework for today, and tomorrow we have time to discuss the group work. So I'm gonna introduce to you the group work. At least, as I've mentioned before, if you form maybe 4 groups or 5 groups, or however, you don't have to do it alone. You can do it together with your colleagues. And these are the main things you should prepare. You can do it either on a bigger piece of paper, kind of poster, and do it by hand. Or if you like, you can also do it on a computer and then try to upload it here. It's the main idea or the main purpose of this activity is that you learn to make a process chain, starting with the key resource on the top and the product or the service on the bottom, and in between the main unit processes, 4, 5, 6, not more. Yeah, like you have seen already in the lecture, and you will also see today, and see what are the key flows. The idea is that you select a product or service made from biomass. Of course, biofuel is one possibility. And then just say a few words. What is the goal and scope? For example, you want to know current technology here in India, and you're interested in greenhouse gases and primary energy. That's it. Or you want a full endpoint calculation of a future bioethanol production from corn stover, for example. Yeah? But at least brief, just answer these questions brief. But secondly, you make this process chain, yeah, with the main resource and the main steps towards the product, and then see at which stages co-products might occur. Yeah? Where you might have maybe animal feed or straw or glycerin. Yeah, you think if and then at least define the system boundaries, which is at least the system boundary at least is between nature. So nature is going in the system boundaries, simplified, and the product is coming out of the system boundary. Everything in between, you have these unit processes where you need to collect the data and make the LCA. Then, of course, what is the functional unit? Yeah, we've heard that the functional unit is the element. On one hand, it's a product, and you just have to describe, is it 1 driven kilometer or is it 1 megajoule of biofuel, or is it a liter of milk? Yeah, so at least define very briefly what is the functional unit. Um, and then think about, because we've seen in LCA you always have to compare it to something else. Yeah? So at least think about what would be the product or service you want to compare it to. You can compare two different biofuels, but of course you also can compare biofuels with gasoline or diesel. Yeah? So this is at least the idea, and if you can put that all on one page, so to say, and this will tomorrow be the starting point, because you present your findings in the group, and then the other colleagues can comment or ask questions. I can give some comments, Professor Sorenda can give comments, so at least we have a little bit of interaction, yeah, and see if we all understand what your LCA is and what are your system boundaries. And then on Monday you can start to collect data already. Okay. Okay, so you don't need any LCA tools or databases, nothing. It's really to get a feeling to make such a process chain. Okay, are there any questions on the group work?
You can divide them in three groups.
Yeah, of course, yeah.
So one group can take up say paddy straw to bioethanol. One group can take paddy straw to biogas, and one group can take up who is working on biobutanol. Yeah, Manisha. One group can take up paddy straw to biobutanol. So starting with the one substrate, three different products,
Perfect, yeah.
and then they can compare with the alternate uses, and definitely a reference may be gasoline, or in case of biobutanol, it may be different.
Yeah, that's tricky, yeah.
Yeah, so at least within groups also they can share their thoughts.
Yeah.
Will it be fine?
Yeah, that's perfect.
Yeah.
Perfect, yeah.
Okay.
So we have 3 groups. Very good. Mhm. Yeah. Okay. So I come to my lecture number 7. Um, Zooming in a little bit more on the methodology of life cycle assessment and its application to biofuels. At least what we've seen, we are going to compare using biomass, and as we want to replace fossil energy, so we compare it to fossil energy, and this is again a graph showing how you do these comparisons. On the left hand side it's the bioenergy system, always starting in nature with growing the biomass. Then you have the different processes and conversion processes. In that case you're providing heat and electricity, and these blue arrows show more or less the flow of the biogenic carbon. Also on the right hand side you see the same picture for the use of fossil energy. But for the fossil energy, of course, you start with the raw oil or fossil energy underground. So the carbon stored underground at least is also extracted, transported until you provide a certain service. But the carbon finally ends up in the atmosphere. Yeah, so you see here, this is at least what's ending up in the atmosphere, whereas the bioenergy in a sustainable way has the possibility that the carbon cycle is closed. We know that on the bioenergy side we have co-products and byproducts, but also on the fossil side you might have co or byproducts. Yeah? The oil refinery also makes raw material for the chemical industry, so at least also on the fossil energy side you might have byproducts. Today I want start also a little bit highlighting land use and the carbon stock stored on land. And globally, the forests, there's a typing error in the heading that always happens. um, the role of forest, because globally forests are decreasing for several reasons, but the forests themselves are really a big storage of carbon. Yeah, because in the trees, in the soil, in the litter, uh, carbon is stored. And it's interesting to see that in the soil and in the living biomass, roughly the same amount of carbon is stored. So really big amount of carbon you don't see it because it's more or less in the soil. And as soon as you start changing the forest, you might also release additional carbon to the atmosphere. Um, um, this is for the general forest, and a big issue is, of course, the tropical rainforests. They even have um, much more carbon stored per hectare. And one big global issue is, of course, the destruction of tropical rainforests. And if you only cut them down and use them once and then make grassland there or agricultural land, in that case, you really lose carbon. And this is a big issue, also relevant for biofuels, especially for the first generation biofuels, because in that case you might have, or you have in most of the cases, a kind of land use change divided in direct and indirect land use change. And this is a very hot issue being discussed the last decade, last 10 years or so. The idea is in your LCA, you maybe start converting a grassland where you have animals in the beginning, you convert that to cropland because you want to produce raw material for bioethanol or for biodiesel. Yeah? And by doing so, really a direct land use change is happening because before you had grassland and now you have agricultural land. And normally in grassland, you have more carbon stored than in agricultural land. Yeah? Um, so this is called the direct land use change because it's one piece of land you convert to another piece of land. But then you see you have less grassland. Yeah, so the animals have less grassland. So it might happen, or it really happens, that of course if we want to have grassland for the animals again, uh, we need to convert, at least as land is limited, convert forest to grassland. Yeah? And converting forest to grassland itself is direct land use change again. Yeah? Also changing the carbon pools. But from the viewpoint of the LCA you're looking, you call the second effect, converting forest to grassland, it's called the indirect land use change. So normally this is outside the system boundary of the life cycle assessment, yeah, in attributional LCAs, but at least you have to consider that if you want the same amount of grassland because you have the same amount of animals, this is called indirect land use change. And there's a big discussion within the LCA community how to include this indirect land use change. Normally, on a global scale, we all know that we convert mainly tropical forests to grassland and later on to 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 cropland, but it's not proven that it's only the biofuels pushing uh, this scheme to convert forest to grassland. There are many other effects. Yeah, for example, globally the population is increasing, so we need more agricultural area for food production. Is one reason. Yeah. The other reason is that we generally want to have more meat. So globally, the meat consumption is really dramatically increasing. And if we need more meat, we need more animals, and we need more grassland. And this has at least nothing to do with biofuels. Biofuels maybe put an additional pressure, so to say, on the availability of cropland. So there is not a direct effect. it's a relatively complex indirect effect to really say how much for land use change is the responsibility of the biofuels. And, and that is at least one reason why indirect land use change has been heavily discussed, and it's also reflected partly in the regulation on sustainability for biofuels in Europe. We have this regulatory framework, and of course there they really try to document or at least to avoid indirect land use change. So this is the direct land use change and indirect land use change. It's really a perspective from the LCA. Once it's called direct land use change within the system boundary or indirect land use change. I show you the same graph or the same message again because um, this if you have a starting situation number one here where you have the animals and a certain area of forest, yeah, so this is what you're considering. And in the first step, if you start to produce biofuels, you're converting a part of the grassland to agricultural land. That's why you see these green drops here. This is the area where you're going to cultivate raw material for first generation bioethanol. And you clearly see that then the grassland is less available. Yeah? And if you have still the same amount of animal and want the same amount of grassland, you go to the third picture by converting the forest into grassland. Yeah, then again, the animals have the same space as they had before the biofuel came. And this is then, at least from the point of view of the biofuel, this indirect land use change. And, and the direct land use change at least is or might be considered in most of the LCAs, but you only do the land use change once. Yeah, you do it, and if you continue growing biofuel crops on this piece of land, you only convert it once. So the effect of losing carbon in this transportation is only happening once. Yeah? And then if you continue making sustainable agriculture there, at least you keep the carbon storage on the cropland at a certain level and maintain it at the same level. Only before on grassland it was higher. Yeah? So you only change it once in the overall system for the first system you build up. And the big question is, how do you distribute this initial loss of carbon over the long following lifetime or production phases of the biofuel? So it's a kind of investment, so to say, in terms of carbon investment or carbon emissions only happening once. And this, to be honest, LCA does not have a very simple answer on that issue. Yeah, you can say I'm ignoring it because it's only one effect. But if I produce really over a very long time much biofuel per liter of biofuel, it's very small. And the good thing in LCA is you can always say I'm not considering it. Yeah, because the most important thing in LCA is a transparent documentation. Yeah, and if you say I'm aware of land use change, but due to the reason of this and this, I excluded this in my analysis. Yeah, and if you write that there, you're totally fine. Yeah. So the most important thing, like in most of the scientific documentations, you just have to write what you do or what you exclude, what are the framework conditions. And, and in most of the studies, this direct land use change is not considered. Even the indirect land use change, which is even more difficult, because the indirect land use change can only be addressed in an economic global model, at least, where you have the population growth, the meat consumption growth, the growth of other agricultural products, the growth of raw materials for biofuels. Everything is in there, and which is a at least far away from the pure from the pure LCA. But still, it's for you. It's important to be aware that this effect is existing, and it might or might not be relevant for your LCA. But this is a quite relevant issue about land and land use change. Just to give you some orders of magnitude, um, how much carbon or CO2 is stored or how much carbon you lose. For example, if you convert Greenland to sugarcane, you roughly lose per hectare 2.5 tons of CO2. Yeah, because the difference is from Greenland to soybeans, it's roughly 3 tons of CO2 per hectare. It's only happening once when you convert it. It's extremely high if you convert the tropical forest to a palm oil plantage. Yeah? This is roughly 30 tons, yeah, per hectare. You're really losing carbon because in tropical forest you have so much um, carbon stored. And if you put that directly to the amount of biofuel that can be produced in the first year on this, if you say I put all this burden on the biofuel produced in the first year, you end up with figures 370, 800 grams CO2 equivalent per kilowatt hour. So this is really a very high value. The gasoline and diesel has 250. Yeah, so it's even higher than gasoline or diesel because these carbon effects are very, very, very strong to be to be relevant in total. But it's an effect only happening once, and after the first year, of course, this disappears because then you don't have any further change in the carbon storage if you do a sustainable agriculture there. And and in Europe, in this renewable energy directive, which gives you the LCA for the biofuels on the European market, they also put some ILUC factors more or less per consensus, and they found out that for bioethanol, due to the growing conditions and the countries where it grows, this indirect land use change is significantly lower compared to biodiesel, because biodiesel is more happening in areas where tropical forests are, and therefore has a stronger effect. And there are many publications on land use change and direct land use change, and some of these publications really show that under worse conditions, um, the different biofuels don't save greenhouse gases at all because of these effects of land use and land use change. So it's really needs the proper framework conditions to make raw materials for biofuels. But this land use change effect, this is on this slide here. They are mainly caused or discussed in connection with the first generation biofuels, yeah, where we use this rapeseed oil, soybean oil, grains, corn, grain, wheat. So at least these so-called food crops, yeah, because they are at least addressed by land use change. As soon as you come to advanced biofuel, yeah, and this is also a key driver for going to new feedstocks, yeah, lignocellulosic feedstocks, because their land use change is not an issue at all. Yeah, so this is at least one key driver to include land use change in this consideration, because this is a clear and big advantage for second generation biofuel. Um, these effects can be calculated. Yeah, so there are some programs available. I've shown you one. I will later in the afternoon go a little bit more into this program. I've chosen this BioGrace program because it's relatively simple to be operated by somebody who is not so involved in that. It's an Excel-based calculation system, and it's relatively transparent and gives you many default data already. Yeah? So you find many data, robust and good documented data, with which you can start to calculate land use change effects. And And so we will see in the afternoon there are many other tools, but this is at least a very, very good one. It's a little bit outdated because it's not valid for the current regulation in Europe, but anyway, it calculates properly and you can always insert your own data. Yeah? But the really good thing is that the calculation is very transparent, very, very clear, and it gives you many default values that give you an order of magnitudes. For example, if you want to calculate the land use change effects. And in the afternoon, I will show you with this program, you can also do the overall calculation on biofuels because all the key elements are there with the necessary input data. And you can use the existing data in there or you can override it with your own data. And I'll show you this in the afternoon. Um, I also show you in the afternoon another model. It's from America, the GREED model. They also have in that model, I also will show it in the afternoon, they also have one specific part in the tool dedicated to land use and land use change. So at least this is a very good way if you're further interested or if this is somehow relevant in your education to work on land use change. These are two programs where you get a very good insight on the orders of magnitudes and the data that are relevant to calculate land use and land use change. So this thematics of land use and land use change is at least very closely connected to the production of biomass, because we've already seen yesterday that it's always a question what's happening on that piece of land if you do not produce bioenergy, which we call the reference use of the land or the biomass. And so these two questions are quite relevant. What happens on an arable land if no energy crops are produced for your purpose? And there are different possibilities that have somehow to be included. And you will see it later on if I show you more process chains. This reference use of the land is relevant, but also of the biomass. The reference use of the biomass is mainly relevant if you use residues like straw, used cooking oil, manure. You always have to think what's happening if I do not make an energy carrier, if I just keep the current usage of it. For example, we discussed yesterday the combustion or the burning of straw in the fields happening around here. Yeah. If you use the straw for something else, you avoid this, and this gives you an additional benefit, of course, of the production of an energy carrier out of straw. Yeah. So this is it's quite relevant, and you will see it in the coming pictures again that this is included. I show you the same picture a second time. I already showed it to you yesterday, but I think it's good to repeat because this is really an essential um, graph to see if you want an energy service from bioenergy or fossil energy. These are the key processes: collection of residues, cultivation of biomass if you're in agriculture, the transport, the processing to bioenergy carrier, distribution of the bioenergy carrier, and the use of the bioenergy carrier. And the fossil system, at the first glance, is at least this more or less the same processes, also transportation, conversion, use, and distribution. But for the biomass, we've seen we have these co-products, and these co-products somehow must be assessed in the overall system boundary. And in most of the cases, you look what is the conventional way to produce this co-product, and if you can avoid that, you can subtract it from the emission of your bioenergy, which we call also the substitution approach, which is one way. Secondly, the reference use of the residues and the area. Yeah, so if what's happening on this piece of land if I do not produce grains, for example, for bioethanol, or what's happening with the residues, with the straw, if I do not make bioethanol, for example. So this is quite relevant. The system becomes really tricky if this reference use also provides you some product, because then you also need on the bioenergy system an idea how you can further provide this product that was provided before by this reference use. So it's really a complicated thing. And these elements you see here, the collection of residues, cultivation of biomass, the reference use, these are the key elements that are relevant for the land use change, directly and indirectly. I've mentioned before. So this is the generic picture that always works. And if you zoom in now for specific applications, yeah, if you say I want, for example, produce electricity from wood chips in a power plant, and I compare it, for example, to a coal power plant, the picture looks more or less like this. On the right hand side you have the coal extraction and the thermal power plant from coal providing electricity, and on the left hand side you're collecting the wood chips, you transport the residues, you process it to wood chips because they need to be cutted or dried, you burn them, and then via the electricity grid you can provide electricity to the consumer. In that case, the electricity grid is included here because here the functional unit is really a certain amount of electricity at the user side. So at the socket on the wall, for example, I want 1 kilowatt hour already on the socket of the wall. Therefore, you have to include the electricity grid. If you define your functional unit just at the gate of the power plant, which is also okay, then you don't have to consider the grid. So this really depends on how you define your functional unit. And for example, if we use sawmill residues for this power plant, the question is what happened to them before you start using them. In that case, it was an Australian case study. On one hand, it's natural oxidation taking place because if a pile of wood, sooner or later it disappears and all the carbon is re-emitted in the atmosphere without energy use, and that has to be considered. It's the same if you take out forest residues directly from the forest. You also change in the carbon storage in the forest because you take out the wood, which otherwise would have lay down on the ground and disappear slowly and release CO2 slowly. If you take it out, you also change the carbon stored in the forest. Yeah? Therefore, this reference use is also relevant considering the carbon storage. But this is at least the picture how it looks like if you make electricity. A more complex one is biodiesel from rapeseed. Compare it with fossil diesel. Still, it's the similar picture again. Yeah, you have here the cultivation of rape, the transport, the proceeding of the rape to rape oil first, and from rape oil to biodiesel, distribution of biodiesel. Here we have a biodiesel bus, and you compare it with a conventional diesel bus. But then we have the glycerin as a byproduct. The reference case is you can make synthetic glycerin out of natural gas. This is the biggest commercial way because we have a quite high demand on glycerin, and that can be made also from natural gas. But if you make it from biodiesel, of course, you avoid the emissions of making glycerin from natural gas. Yeah. Secondly, the animal feed. Yeah, it's an animal feed. It avoids the cultivation of another animal feed. In that case, we've taken the cultivation avoided from soy feed production, which is quite relevant for the Austrian and European situation because we are importing very much soy feed, mainly from Southern America, to Europe. But if we make our own biodiesel, we really make our own animal feed, and we really substituting or avoiding the import of soy feed oil. So we are avoiding emissions that might occur in South America if we now make our own animal feed. Yeah. So this is very close to reality to really see what's going to happen. And this reference use of the area in the past in Europe we had an overproduction in the agriculture. Yeah? Therefore, the farmers got money doing nothing on the field, yeah, to keep the make it a set aside land, yeah, because then the prices keep kept at a certain level. Otherwise, they would decrease too much. So the farmers really got money doing nothing on their field, yeah, which is from the point of LCA the best way, because that's the easiest way to include the land use, the reference land use, if it's a set aside land. So at this time, this was also a key driver on the beginning to introduce biofuels, because there was agricultural land left. But this situation now really changed. Yeah. We don't have now it's the other way around. We are still lacking on agricultural land due to several reasons, but the economics was a little bit different in the past. Yeah. So you see again, this is for biodiesel, and in all these graphs, it's very important that in these eclipse you need an equilibrium, so you get the same amount and quality from the left-hand side system and the same amount and quality from the right-hand system. Yeah, the same amount of animal feed with the same nutrition content, and, and the same amount of glycerin with the same quality, with the same pureness, and transportation service, of course, a certain distance, the same, and of course also on the area, the same amount of area being used on both sides. So this is a way to control if your system boundary and setting up of the system is really in line, and for the calculation you need the same on both sides to have an equilibrium. Yeah, that's the way you can read it. In some cases, we have seen that for the co-product, you can also apply, for example, energy allocation. Yeah, that would simplify that picture a little bit, because then you don't need these reference uses of the glycerin and the animal feed on the right hand side, because you just subtract, or you just give the energy weighted part of the emissions for the biodiesel on the left hand side. That makes the LCA a little bit simpler, so to say, which is also okay. Yeah? So you can always apply energy allocation also to this product. Just specify and write it down. I applied energy allocation using these heating values, give you a share of 50 to 60 or whatever, which is then allocated to my bioenergy carrier. I have two more examples. As one simple example is the next one. It's a comparison of a wood chip boiler to a reference system with an oil boiler. In Austria, we had many oil heating systems in the past, and we put much effort to really substitute raw oil heating, because we're a cold country, so we need a heating in winter. Nowadays, really, oil heating systems are forbidden in Austria. So you're not allowed to build a new house and put in an oil heating system. Yeah. Now we are going also to forbid natural gas for heating, because it's fossil based, and it's so easy to build a house which needs less energy first, and then power it with biomass or power it with a heat pump, which is much more sustainable. So in the past we made many comparisons showing that the heating with wood chips is much more um, environmental friendly than heating with oil. And this is just one example, again, using forest residues. As we have so many forests, we have many forest residues which otherwise would be left in the forest. Yeah. So there was no use for the branches and the top, so they have been left in the forest. But if you also take them out, you have a good fuel, a renewable fuel, to supply renewable heat to houses or communities. And the last one is just uh, the most complex one, I would say, because so bioenergy itself is already relatively complex in terms of LCA, and the biogas and the biomethane within bioenergy is even one of the most complex ones. And so I'm happy that one took the biogas for the work also for tomorrow. But maybe this is not so complicated because you have only one feedstock. Normally, for biogas, you use different feedstocks. Yeah, and the more feedstocks you use, the more difficult it became. In that case, we use corn or maize as a starting point, which was also or is still common in Europe, because from 1 ton of maize you can really make much biogas. But on the other side, corn is a food or feed, so the same debate with like for bioethanol, and we comparing electricity and heat. We compared that to electricity coming from the natural gas power plant, and the rest is a heating system using oil. So in that system, we use first cultivation of maize. So the question is, what is the reference use of this piece of land? It's in that case set aside land. Then additionally, we had also substituted cultivation of maize as an animal feed. Yeah, and if we do that, we are lacking of animal feed. Yeah, because if we now use the corn for biogas, so we have the animal feed again, and to replace this animal feed, we're going back to the cultivation or the import of soy feed. So now the soy feed appears on the other side of the bioenergy system, because we are using the maize not for food and feed, we're using the maize for biomethane, but we still have to make sure to provide the same amount of, of animal feed. Then we also put grass in. We also put grass in the biogas facility, in the biogas plant. Yeah, the grass before was just composted. So there was at least just a composting, but the composting gives you a fertilizer. If you compost, you also do that in organic farming. If you compost something, all the nutrients are there and you can reuse them. So the composting gives you a fertilizer. The good thing is that also the digested material coming out of the biogas plant also is containing fertilizer. Yeah? So on the first glance, you also get a fertilizer. You not get it directly from the composting of grass, you get it a little bit indirected from the biogas plant. So this is very important that the fertilizer balance is kept. And then we have also put in manure, yeah, in the biogas plant, which is very good because manure contains much water, and then you have enough water in your biogas system that the anaerobic process is working quite well. If you don't digest the manure, you just store the manure, and again the manure has a fertilizing component. Yeah, you bring in the fertilizer. This is not lost. If you put it in the biogas plant, you get the same amount of fertilizer, more or less, out of the biogas plant. So at least the fertilizer balance is quite the same. If it's a little bit different, you have to add here on one side also the production of maybe of mineral fertilizer. Yeah? And you see here, this already looks relatively complex because of the different feedstock, and each of these feedstock has a reference use, and this reference use also provides you a product. It could be animal feed, it could be a fertilizer, and that really has to be reflected again in the overall picture of the LCA. And again, in these red eclipses, there's an equilibrium of the quality and amount of fertilizer, of grass animal feed area you get from one side. It also must be the same on the other side. Yeah, so again, you can check in your calculation that it's the same on both sides. Um, when you store manure and not digest it, the manures, also in the manure, they're starting an anaerobic process when you just store it. Yeah? And you release relatively big amounts of methane from the manure storage. Yeah? And in that case, for example, if you avoid the storage of undigested manure, you also avoid these uncontrolled methane emissions, which gives you also a big environmental benefit. So digesting manure in a biogas plant, yeah, is a very good thing to reduce greenhouse gases. And this I will touch on the next slides, that in agriculture, methane emissions and nitrogen oxide emissions are very strong emissions coming directly from agriculture. So they are also reflected here in the LCA. So if there's a possibility, like here, for avoiding the storage of undigested manure, it's a good way, and you count that in this box of storaging manure, you have a negative, finally a negative methane emission, because you really are able to avoid these methane emissions. So I'm telling you a little bit now also about the greenhouse gas emissions that occur directly in agriculture, because that is also relevant to understand in the LCA. So the agriculture is having, on one hand, CO2 emissions from soil preparation. You might have, they have methane emissions from the animal housing, or for the animal housing the animals, and you have these N2O emissions, which are relatively relevant on a global scale, but also on national scale. The N2O emissions are mainly dominated by the agricultural sector, yeah? Because these N2O emissions from fertilizing agriculture really are a strong contribution to the overall N2O emissions. And globally, it's nearly 90% or even more directly coming from agriculture. It's similar with the methane emissions. Yeah? Also, the methane emissions to a high share, also more than 80% or 85%, directly coming from agriculture. Yeah? That is part of agriculture. That's why I want to show you um, this a little bit more in detail. And you see here, these are the nitrogen sources uh, globally in or it's in Europe. I'm not sure if it's in Europe or if it's globally, but you see that the agricultural soil management has a substantial contribution to N2O emission, because in agriculture you need nitrogen that things are growing. That's a very important fertilizer. But as soon as you put nitrogen on a field, and it does not matter if the nitrogen is coming from manure or from grass, or if it's minerally based nitrogen, you always have an effect that a part of this nitrogen is directly converted on the field to N2O emissions. And this is at least the pity behind that. The process I've shown you here is very complicated. Yeah? The process of this N2O formation in agricultural soil, that's a big thing. So I even don't understand all the details. For me, it's only relevant to know how much N2O finally is going directly to the atmosphere. Yeah? And what we in Austria, for example, on a hectare of land in agriculture, you have per year 2 to 5 kilogram N2O emissions per hectare. 2 to 5 kilogram. You don't see them, you don't hear them, you don't smell them, but on the agricultural area, depending on the season and everything, but at least on the end of the year, between 2 and 5 kilograms of N2O is directly emitted on this piece of land. And the CO2 equivalent factor of N2O, I don't know if you remember, it's 300 times stronger than CO2. Yeah, so if you emit 1 kilogram of N2O, it's equal emitting 300 kilograms of CO2. So if you have 2 to 5 kilograms N2O per hectare, and you put that on the CO2 equivalent level, it's 600 to 1500 kilograms CO2 per hectare and year, the emissions from agriculture. And this is really a strong part, and we will see later on in the biofuel assessment that these N2O emissions show up also in the final results. And therefore, it's so important to know, to understand the effect, and also to quantify that when you do the inventory analysis. And in most of the cases, there is a relation between the nitrogen input to the field and the N2O emission output. It's a relatively good estimation, so many formulas calculate this based on the nitrogen you put in. But the overall complex system is very complex. It depends on the water content, if it's raining or not raining, and many, many things. But the N2O emission finally is a very relevant source. And here you see some examples for the N2O emissions, and also to really avoid these emissions is very difficult. Yeah, so because it's a process taking place anyway. Yeah, it's even all the food we consume, they all have. So if you make a balance of a salad or a vegetarian lunch, yeah, it's all grown in agriculture. Even all these products roughly have half the greenhouse gas emissions in life cycle assessment from this N2O emission in agriculture. Yeah, you cannot really avoid them. And if you once use or need an N2O emission factor, the International Panel on Climate Change is providing a good database for all the national inventories. Yeah, and this is always a good starting point. You find many emission factors in this IPCC reporting, very easy to find. You find them for oil, gas, N2O, coal mining, or whatever. So this is a good initial source, because these factors are also used for the national inventories. And there you find, for example, for sure an average N2O emission for the agriculture in India, which might not be valid maybe for the field outside, but still it's a good national average. If you know more about the fields you are considering, of course you can further modify it. If you don't have that, it's best just use the average Indian value you will find in the greenhouse gas balance of your country, which is at least a relatively reliable and meaningful value. And secondly, agriculture is also much responsible for methane emission. Yeah? And methane emissions from, this is the overall balance, at least methane emissions in agriculture depend on the animals, to say it simple. Especially cows, they're producing much methane. Yeah? You know, they have to re-eat. I don't know the English word, but they always uh, they have to, their digestion needs much eating, and they have to beat it again and again, and they producing much methane on both sides of the cow. Methane is coming out, and then also in the manure management you have this uncontrolled um, methane formation, because it's a wet stuff, and in that wet stuff you have anaerobic areas where methane is emitted. And here you see that roughly 75% come from the animal itself. It also comes from other animals, but cows are quite the most dominating one. But in the manure, um, you also have much methane emissions. And this is good to be here because you're all vegetarian, yeah? Because the vegetarian really avoid all these emissions. And these emissions occur, of course, with all the meat, but unfortunately, with all the meat, with all the animal products like milk or yogurt or so on. So in the balance of milk, yeah, you find very much methane coming from the cow, yeah, in the overall LCA. Yeah. So still, this methane you find in all animal-based products, and they are also very much dominating the overall greenhouse gas, balance. Secondly, so beside what's happening in the cow, yeah, from the different feedstocks you see here meant so the cow is most dominating. It's not the chicken and not the pigs. It's mainly the cow for milk and for meat, having 60% or 65% of the global emission really come from the cow. And secondly, methane is also emitted in rice cultivation. Yeah? Because rice is growing in water, and in that water you also have anaerobic processes, and therefore also the rice production That's because it grows in water. You cannot change it, so to say. So also the rice production, and the rice has certain methane emissions. I never made an LCA on rice, so I cannot say how much 1 kilogram of rice is having on greenhouse gases. I have no clue. That would be once interesting, just to get an idea how much it is compared to potatoes or grains. Yeah, I don't know, but we know, of course, that it's an anaerobic zone where you have these methane emissions. And this is even a more detailed picture, but it summarizes at least relatively well here for the N2O and the methane emissions, where in the different activities, agricultural activities, you have this methane and the N2O emissions. You also have methane emissions when you bring, for example, manure, if it's digested or not. Anyway, if you bring the manure on the field as a fertilizer, you also have on the field methane emissions, still, and N2O emissions. So you see they are happening on different places in agriculture, and the processes behind are relatively complex because it's all natural based, and it really depends on the framework conditions. But still, the emission factors provided by the International Panel on Climate Change, these emissions factor at least give you a good estimate for the different emissions in the different areas in agriculture. Okay, so this is my final slide for the morning session, the take home message. You see here again this picture, we call it at our institute the left and right picture. Yeah. So in LCA at our institute, we always, when we start doing an LCA, we ask, did you do already the left and right picture? This means exactly like this. You have one system on the left-hand side providing the same services as a system on the right-hand side. And the right-hand side at least describes the reference system. It might use fossil energy, might also use other energy carrier, but in that case, you need the same energy service on the bottom from both sides. You have to consider the reference use of the area and the reference use of the residues, like used cooking oil or straw, and of course the co-products of bioenergy. I hope I could explain you the understanding of land use change, indirect land use change, and direct land use change, that these are relevant effects that can be included in LCA but must not always be included, and only the direct land use effects are really part of LCA, where indirect effects are even much more complicated and not directly part of LCA. We've also seen that considering the biogenic carbon pools and cycle, where you store carbon in soil, in plants, in litter, is relevant in the LCA as soon as you start changing these pools. And finally, we learned about the N2O emissions and the methane emissions associated with agricultural practices, that they are happening, and at least showing you where in agriculture these emissions occur. So I'm ready for this morning session, and I'm still here to answer any questions. Thank you very much for listening. So everything was clear? Okay.
Yeah, thank you, Dr. Garfred. And again, I think this is the key slide which we are seeing in the last take-home message slide, also the key figure. And everybody tomorrow will be, better you prepare one small PPT, 5-6 slides on the activity. This all the slides of our expert I will be sharing with you. So just go through it and try to have a, at least understandable, LCA about all the three aspects which we are taking. And in the next session, we will have 5-10 minutes instructions here, and then we will take up like uh, one bioethanol practical kind of thing, that is a key step, that say how do we go for saccharification of biomass, and Dr. Vikas Beniwal will be taking that. So we can break for tea and session, hands-on session on estimation of lignocellulosic enzymes. So since this is a program on biofuels, and bioethanol is one of the important component, and in that too saccharification is one of the important step in the bioethanol production, where we concentrate on the conversion of lignocellulosic biomass into reducing sugars, and that ultimately decides the economy of the overall process, that how much of the sugars we are able to get after the saccharification process. And then finally, if it is the yield is good, saccharification efficiency is good, then we'll be able to get good amount of ethanol converted by the Saccharomyces. So to take on this hands-on session, we have Professor Vikas Beniwal, our esteemed head of the Department of Microbiology, and he has got research interests of industrial microbiology, enzyme technology, and bioremediation. And he is serving as a professor at our department since 2022. Prior to that, he served at different position in DU Maulana Ambala, uh, and before that also he has got vast teaching experience, starting from 2003 until now, you can call around 22 23 years of teaching experience. And if you talk about his educations, his BSc from Rajasthan Agriculture University Bikaner, and MSc from GJU Hisar, and PhD again from GJU Hisar. And if you look at the citation profile, he has got more than 100 publications, including research papers, book chapters, one book, two patents, and he has completed one research grant also. And overall citations is more than 2000, with an H index of 22. And he has guided 7 PhD students, and one is or two students, they are undergoing PhD as of now. So I welcome Dr. Vikas Beniwal for this practical session in this GIAN program, and really thank to him for sparing his valuable time. So I request Dr. Vikas to take the session. Thank you. Uh, so, thank you, Dr. Professor in absentia, for the introduction, and good morning to all of you. So today we will be going for the practical session of cellulase activity, cellulase enzyme activity, and before going to the practical session, just go to the basics. We want to go through the basics, that how we can estimate the activity. So we will be going through that, and then we will be following up in the lab with this practical session. So the topic is estimation of cellulase activity. So before going to the cellulase activity, as Professor Surinder Singh was saying, that main motto is to convert the lignocellulose biomass into bioethanol. The first step is sacrification of lignocellulose biomass. So before acting the enzyme, let's understand the
plant cell, as you all have gone through that plant cell wall, if we talk about, or we talk about the plant cell. So this is the structure of overall, you can say, plant cells. And if we talk about the plant cells, they are combined together. We call it as middle lamella. Mostly it's contain of pectin and other oligosaccharides. Then basically comes the primary cell wall. Then comes the secondary cell wall, and we all know that the primary cell wall is made up of microfibrils, and this microfibril contains the cellulose basically, and along with the secondary cell wall that also contains cellulose and hemicellulose, lignin and xylin, along with this I can say cellulose. So all these constituent of polysaccharides are there, and we are interested to convert these polysaccharide into monomer, or more specifically we call it as reducing sugar. So our main focus is towards the cellulose, to convert the cellulose into monomer in terms of glucose, I can say, and then we can convert the glucose into ethanol by Saccharomyces cerevisiae. So this is an overall representation when we can say that overall cellulose composition in the cell wall is around 30 to 60%. It varies from sources to sources, and next one is hemicellulose. It contains around 15 to 35%, followed by lignin and then pectin. So these are the constituent, and we will be following the cellulose part in this. So cellulose degradation, if we talk about, we have three basic enzyme. If we talk about, we have exogluconase, we have endogluconase, and we have beta glucosidase. So there are three enzymes we will be talking about if we are talking about cellulose activity. And the first one, if we talk about the structure of cellulose, cellulose structure is a polysaccharide, we all know, made up of a repeating unit of glucose, we all know that, and the joining link is beta 1,4 glycosidic linkage. So our main purpose is to break this beta 1,4 glycosidic linkage, so that we can free the glucose, and then we can use that glucose to convert into ethanol. So to break them, the first, as I was talking about, the first one is glucanase. We call it as endo and exo basically. So exo act on the terminal basically. So we have a reducing terminal. If we talk about, we have the non-reducing terminal. It act on both the terminal, and as a result, it give us cell bios. Cell bios is again a oligosaccharide. More specifically, I call it as a disaccharide. So we are getting disaccharide linked by beta 1,4 glycosidic linkage. And if we talk about endoglucanase, so it's basically, as the name suggests, it's acting in intermediate basically, and it's breaking the chain in between. So when the endoglucanase is acting, we are getting various oligosaccharides, and our main purpose is then further to break down the oligosaccharides into monosaccharide, or into reducing sugar basically. So both endo and exo, they are giving us disaccharide and oligosaccharide, and then comes the activity of beta glucosidase, and then when beta glucosidase comes into the picture, then it breaks all the oligosaccharides and disaccharide, and we are getting the individual sugar that we are interested in. And finally, when we have the monomer, or reducing sugar, or in simple you can call it as glucose, now it is available to be converted into ethanol. So this is an overall representation that how we can go for cellulose degradation. Then as the topic was to estimate the cellulase activity, so we are going towards the protocol, and you will be doing, most of the students, I think some of you have the PhD title also related to this topic, so you are doing routine work. Some of you have not gone through, so you will be going in the practical session. Just I am giving a hint that how you can estimate the cellulase activity. Initially I am talking about endoglucanase activity, cellulase activity in other terms we talk it about. So we are using CMC as a substrate in that case. CMC stand for carboxymethyl cellulase. As we all know that cellulose is insoluble. So it contains a carboxy group, and that carboxy group makes it soluble. And unless and until a biomolecule is not soluble, we can't convert it into a ethanol, or we can't act upon more specifically with the enzyme other than if we talk about lipases. So carboxymethyl cellulase is there. So we basically take the filtrate and we incubate the filtrate. If I am talking about the culture filtrate, so we incubate the filtrate with the CMC cellulose 1%, that is the substrate, and then further we incubate for 30 minutes at 50 degrees centigrade. After incubation, our main purpose is to find out how much sugar is liberated, how much sugar is released. In other terms, we want to know the reducing sugar. So in that case, we use dinitrosalicylic acid, as it is called 2,3,5-dinitrosalicylic acid. It converts into 2-amino 3-nitrosalicylic acid, or salicylicate, I can say. So this is the conversion of you can say uh, this dinitrosalicylic acid that facilitates the identification of you can say the sugars. So once the densa is added, we boil for 15 minutes, then we make up the volume to 20 ml, and at final stage we go for the OD at 540 nanometer, and more the reading is, more the reducing sugar is. So basically it tells about how much sugar is released, and this is more specifically done in case of I can say endoglucanase activity. Another one is we are interested in the second activity, that is beta glucosidase activity. So as I have told you earlier that you have endo and exoglucanase activity. So you are more interested that once you have oligosaccharides in your hand, then you want to convert them into monosaccharides. So for monosaccharide, the linkage is targeted, and we call it as beta 1,4-glycosidic linkage, because cellulose is made up of 1,4-glycosidic linkage, and even the degraded you can say oligosaccharide, they all contain beta 1,4-glycosidic linkage. So to see the activity of beta 1,4-glycosidic linkage, we go for again glycosidase, beta 1,4-glycosidase activity basically, and our target is the linkage. So in that case, we take the substrate, that is para-nitrophenyl beta D-glucopyranoside, and as the name suggests, a phenyl group is attached as a beta 1,4-glycosidic linkage. So rather than a sugar, a second member is a phenyl group. So once there is a beta 1,4-glycosidic linkage, the phenyl group will be released and will be used for the production of color, that is used further for estimation of enzyme activity. So now if we start the procedure, it start with 0.5 ml culture filtrate, and then again we are adding equal amount of the substrate, it is again 0.5 with 5 millimolar, and then we are incubating it at 30 minutes again for 50 degrees centigrade, and then finally we stop the reaction by adding 1 ml of 0.4 glycine buffer with pH 10.8. This buffer works in two ways. One is it's inhibiting the activity of beta glycosidase. Another one is it helps in formation of the color. The color is due to the release of phenyl. So the phenyl is released, and at alkaline pH it is giving you a color. That the color is now measured at 430 nanometer. So more, again I say, more the color it is, more will be the activity. So these are the two enzymes we will be talking about today. We are not going towards the exoglucanase activity. So only endo and this beta glucosidase, we are talking about this in a lab. So hopefully it is clear to all of you, and we will be heading towards the practical session for this, right? So we will be heading towards the lab for this, right?
Okay, so now we're gonna see how the methodology of LCA is applied to biofuels. I show you some examples, and even if maybe you have the impression so far that it seems to be so complicated to make an LCA on biofuels, I will show you now it's not so complicated, because if you do it properly, if you're transparent, to take reasonable assumptions, you really can judge and find out what are different environmental effects of biofuels. And as we've learned on the very beginning of this week, again, to remember, when we talk about transportation fuel, you always have to be careful to define and specify the system, especially what is the raw material, what is the conversion, and what are the transportation biofuels you are considering. Um, Secondly, it's very important that you specify the system you're considering very well. And the examples I'm going to show in the following was part of this big project I've shown you already yesterday on the internet, with these 30,000 vehicles we have analyzed. And what I'm showing you is the background work we did before we could do it for these 30,000 vehicles. But also in the link from this database, this documentation, you find many of the descriptions that are relevant also for biofuels, and to understand the things I'm going to show you today. Um, from my practical experience, from it is with this LCA, very important to try also to summarize the key information in a brief way. We have seen that for the biorefinery with the biorefinery fact sheet. We also develop here, we normally do it in most of our LCAs. You always have to make a summary for communication and an executive summary. And again, you see here, this is a fact sheet of biofuel. We will go through that in the coming slides. But the idea is really that on this one pager, you find the key information you need to understand what is the framework condition, what is considered, and what is the result. Um, and what you find here is, on one hand, the process chain you're already familiar with. You also see the main data assumptions in the upper part, so the key data. We need many data, but finally, on the very end of the LCA, you know which are the key data that significantly influence the final result. We discussed yesterday about the driving energy consumption. If you go a hill up and down, or if you're in a flat area, for example, the energy consumption is one of the key data when we talk about transportation systems. So this data must be here, saying I need so many liters per kilometer for the vehicle I have considered. But it's also relevant what is the size of the vehicle or what is the size of the battery. At least also to identify what are the key and the main influences. And finally, of course, the more you have graphs, yeah, and pictures telling you the results, the easier it is to get a quick overview. So this is at least the summary, and I go it now step by step by going through this fact sheet. I start with the fact sheet on ethanol. We have also seen that picture starting in nature on the upper part, stopping with a transportation service on the lower part, and in between are the key processes, unit processes you need to convert the raw material to a transportation service. And in purple, you also see some byproduct that might occur and how it is handled. It means an internal combustion engine using ethanol, and the mix means it's a feedstock mix. Because in that case, we analyze the average European feedstock mix today, in future, and in long-term future. So depending on what is the feedstock for ethanol, of course, also the results are there. And there we have also in future a certain share of lignocellulosic bioethanol included in that mix. And there are scenarios based in the background. We took them from existing scenarios we have in Europe. So in our documentation, we just refer to a scenario saying this scenario says we will have so much lignocellulosic bioethanol. That's why we assume a share of 10% lignocellulosic or even more. Yeah. And and then in the upper part, beside the process chain, maybe you can. It's difficult to read the numbers, but it's not so much on digging in the single numbers. It's just to tell you that this is a written explanation about the system. Is this box over there? And in these two tables here, you find the main foreground data. And at least there may be 10 or 15 key numbers, yeah, that you have to know to understand the results. And this white table here already is a result table, but I show it to you in the graphs we are producing. So one of these graphs is it's the fact sheet, the lower part for bioethanol results, and in this part here, these are the greenhouse gas emissions. So this is information about the greenhouse gas emission, and this is information about the primary energy demand. So in that project, we have a strong focus on these two, and here you see the greenhouse gas emissions per driven kilometer. Yeah? And this is for today, this is for 2030, and this is for 2050. Yeah, so you see there is a decrease expected also in the energy efficiency in the years to come, in the next 5-20 years, how it might develop. Of course, there are assumptions behind that, but at least we expect a decrease. Additionally, as I mentioned, in some cases, it's really useful to use a range in the results, not to, LCA is an estimation of the impact. So if you end up with a range, with a reasonable range that at least makes sense, but you still see the difference in future is significant. It really goes down significantly. Secondly, you see here in these two graphs, you see this bar is the total value, yeah, which is also appearing here. And the other parts tell you where the emission occur in the process chain. Yeah? And you see this is the cultivation, the transportation, the processing, and the vehicle itself. Yeah? So at least this gives you a more detailed information which of the processes is most relevant. And in the upper part, you see that the two big bars are the cultivation of the feedstock. And this yellow part is the N2O emission. So we learned this morning that N2O from agricultural production, and here's much grain and corn involved. You see even more than half of it is N2O emission. Yeah? And also in the final result, this is the total number. Yeah? You see here finally 15% is from N2O, mainly coming from the cultivation sector. The second biggest one is the processing. Yeah? Most of the current plants, they use natural gas for processing. So the processing is the next big one. And in the processing, you see a negative value for the N2O. Yeah? So the yellow one is a little bit negative. This is due to the fact that in the bioethanol facility, you produce animal feed. And this animal feed substitutes soya feed made, for example, in Southern America. And you get a credit for that because now you make your own um, animal feed. So in the processing step, that's where we subtract at least the emissions, and in that case, the N2O emissions are bigger from the substituted soy feed compared to the N2O emission in the processing. And at least, so this is really the information where the main emissions occur. So for biofuel, it's always the feedstock procurement or feedstock cultivation, and the most of the times the processing. And then these pie diagrams give you an impression about here you have the impression of it's the same like here, but the blue one tells you this is the cultivation part. I don't see the hood here, so I have to keep staying here. Yeah, it's the blue bar here we have summarized. This is the total fuel supply from cultivation to the filling station. Yeah, and additionally, the red one is the emissions from the vehicle production. Yeah, so we have split it here in the supply of the fuel to the vehicle and the vehicle production, and the green one is the vehicle operation. So you see the vehicle production here roughly has 15 to 20% is really only the vehicle production. And this green part, as the ethanol combustion is so-called CO2 free, so it's counted as zero. But when you burn ethanol in a combustion engine, you still create methane and N2O. Yeah? And this at least contributes still to greenhouse gas emission because they're coming from the stack of the vehicle, and in total they make roughly a 5% is methane and N2O. 20% is the vehicle production, but 80% is the supply of the ethanol to the filling station. The pie next to it gives you the share of the greenhouse gases. The blue one is the CO2, so it's the most dominating one, is really the fossil CO2 from all the different processes in cultivation, in the fertilizer production, in the transportation processes, in the vehicle production. So it's roughly 35% is CO2. A little bit methane is always involved, but a significant share of N2O, which is the yellow part. And this is at least also a minimum that for biofuel systems you always have to consider the CO2, the methane, and the N2O. And you normalize it, CO2 is 1 CO2 equivalent. The N2O we heard this morning is close to 300 per kilogram. So 1 kilogram N2O is 300 kilograms CO2 equivalent. And the methane is in the range of 25 to 30. So 1 kilogram of methane has the same global warming effect in 25 to 30 kilograms of CO2. And finally, you summarize them as a CO2 equivalent. And this gives you at least the information which gases are involved. The list of greenhouse gases is really long, but in these systems, at least these are the key gases. We have analyzed all the other gases. They do less than 1% in the final result. So we skip them normally, yeah, because they are not relevant. The same on the primary energy demand. The first pie is at least telling you where you need most of the energy. Most of the energy in that case is also the supply of the biofuel to the filling station. The production of the vehicle, the red one, is roughly 7%. And for the vehicle itself, for the operation, the light green one is 1%. This means all the maintenance parts are also included, yeah, because a vehicle needs some maintenance, new tires, new engine oil, and so on. And they are also included not only in the primary energy demand, but also in the greenhouse gases. The last one is the most important one because the green and the black tells you that the primary energy, the green one is the renewable energy and the black part is the fossil. And you see there it's roughly 60% is coming from the feedstock, which is renewable, but still roughly 40% on fossil-based. The red one is normally nuclear, and if you use municipal solid waste also for electricity or heat generation, that's normally found as others. It's the red one. But very important here, more than half of it is renewable, but still there's a certain share of, fossil energy. So at least this is what you find as a result in this analysis. I show you that the same results also for biodiesel. It's the same, more or less a similar process chain, again using a raw material mix. A raw material mix we currently have in Europe and will have in Europe, again seeing the co-products, and finally, again in the fact sheet of biodiesel, you see the improvement potential of biodiesel in future is maybe not so impressive compared to bioethanol. The main reason is for the bioethanol you can use lignocellulosic bioethanol, straw and wood, which has a much better greenhouse gas balance than conventional bioethanol. But for biodiesel, we don't have such a feedstock. Yeah? So this is still oil and fat based, and improvements there. There are some improvements, but not so much. Impressive to see here that the oil crops, especially rape, they have a high demand on nitrogen fertilization in agriculture. Otherwise, the rape would not grow. So you see here that the N2O, maybe you see it here best, the yellow part, the N2O is roughly 1/3 of the final results is coming from the N2O emission. Yeah, so this is really a substantial contribution from the direct N2O on the agricultural field. Yeah, so in that case, because rapeseed is the most dominating feedstock here, but even the soybean or sunflower is still a relatively high share. But you also see that for the bioethanol, for the biodiesel, the share of renewables is nearly 3/4. Yeah, so this is a little bit higher than for the bioethanol because the energy demand of making biodiesel and the electricity demand is much lower compared to bioethanol. Because in bioethanol you need the distillation of the pure alcohol, and that really needs energy to evaporate and get rid of all the water. Again, for the overall picture, the blue one is the fuel supply, the vehicle production, and the vehicle operation. It is very important to know that the diesel vehicles have significant higher N2O emissions at the stack of the vehicle than the gasoline cars. Yeah, so here the green one is a little bit bigger because the N2O emission from driving a diesel car is quite is higher than with a petrol car. So this is very important to really include also the emissions from the stack. And this is just a summarizing of many different biofuels. In the overall project, we have analyzed, I think one is the diesel and one is the, I have to check, no, they are all biofuels, but also biofuel blendings. And the expectation is at least that they all will decrease in future. And the key driver for reduction of greenhouse gas emission is, of course, that the vehicles are expected to further increase the energy efficiency. So if they need less fuel per driven kilometer, this is one of the key driver that really brings it down. And the vehicle we have considered here is an average vehicle, an average sized vehicle. If you take a bigger one or a smaller one, of course, the lines will go up and down. Additionally, as I've mentioned before, I just show you also the table in some more details, that finally, when we are going to document our results, we tend really to use ranges. And we have specific methodologies to define some reasonable range to avoid artificial differences between two systems. So if the areas overlap, you see there's no significant difference. But if it's a bigger difference, of course, then it is good. I jump over the e-fuels because I think they are not so relevant in your country in the years to come. If you're interested on that, I can maybe later on, if you have a specific interest how to do it with e-fuel, we can do that. But I keep within the bioethanol. The only thing where bioenergy and e-fuels are somehow connected is only when you take CO2 from a biomass combustion. Yeah, if you take that, then you have a direct link between bioenergy and e-fuel. If you take CO2 from air or for any other source, it's totally independent, the e-fuel. Um, as you're interested in also work on specific processes in making the bioethanol from wood, um, you know that the process maybe already better than I do. You know that the difficult thing is really to make the sugars from the cellulose. There are many different pretreatment methods and how you do it. And we're demonstrating these technology also in Europe, but so far we have no commercial breakthrough. Yeah, so there are many enterprises in Europe that trying to develop this process. We have in Denmark a big facility, we have in Germany a big facility, and we have in Italy a big facility, but they are all still on the demonstration pilot phase, because to really keep that constant production process is still a challenge. Yeah? And really the making the sugars is a big thing. And then normally in the current demonstration plants they use the lignin to supply the heat and electricity you need for the process. You have seen this bigger picture already in different ways, always telling the same, how to come from wood to bioethanol. As I mentioned before, also the black liquor from pulp and paper production, depending on their specific process, you might have the possibility to also use the sugars from the black liquor, and afterwards you still can use the black liquor for electricity and heat generation. I told about the example we have in Austria. You know the composition of wood and straw. You know how much sugar you can make from different lignocellulosic material, from beech, from hardwood, or from grain straw. And for us, at least in a bigger project, we were thinking about, can we integrate this lignocellulosic bioethanol system in an existing pulp and paper mill? The idea was they have already lots of wood being used for pulp and paper. So for them, it's easier. They know the wood handling. They know where to buy the wood. So for them, they have the perfect infrastructure to also use that. They don't have only access to the resource. They have the existing logistic. They have the infrastructure. And very important, they have the people there that are used to run an industrial facility, because you need people that are trained to run systems like this. And in the pulp and paper industry, you have the engineers that are able to run such a facility. And at least in their overall system, they have quite good opportunities. And this was a project together with the Austrian pulp and paper mill, and we had two case studies analyzed in detail. And this is the biggest pulp mill. This is very close to my hometown. It's only 20 kilometers away, and we used that as a one case study. And this is roughly their energy balance. And the nice thing is also, in the last years they have much waste heat. In winter in Austria it's cold, and now they build a district heat pipeline with hot water to bring the heat from the pulp and paper mill to the city of Graz, because we have a district heating system. And that is very attractive, because otherwise they had to cool it away and the heat would be lost. But now they have built a pipeline to Graz, a pipeline with hot water in it, not with oil, a pipeline to Graz where we can heat the houses in Graz. So this is a very good way of using all the products. We've learned a biorefinery should make a value of most of their products as far as possible, so they can also have converted the waste heat into heating value, into heat that can be sold on the market. And the sustainability assessment in that specific study was a little bit broader than only focusing on the environmental part. We looked here first on the technology. Yeah. First, you need a technology, good mass and energy balances, and a reasonable system that really seems to be able to work, especially with lignocellulosic biomass. You need to think, do I make a big one or a small one? What are the mass flows? What are the efficiencies? What are the yields? And so on. How much water do I need? And so on. So it always starts with technology first. Next step is to look on the economy. Yeah, to say, okay, the economy must be really offer a business opportunity. Otherwise, it doesn't help if you have an LCA for a system that is economically or even technically not possible. Then it's lost time and lost money, so to say. So we really started first with the technology, then with the economy, and then with the environment. Yeah, when we have specified the systems and discussed also with the stakeholders, with the pulp and paper industry. We have 15 pulp mills in Austria because we have much forests. We also have much pulp and paper mill. So then we made this environmental assessment, and finally also the social aspects, yeah, because you also need to involve um, the public acceptance on one hand, to see how many additional jobs you are creating if you make additional value there, but also in securing the production location. As I've mentioned, the paper demand is going down, so the pulp mill has an interest to have new products, that they can keep their production facilities, that they can keep the jobs there, keep people employed, because industry environment is always changing due to market and different development. So this aspect was very important, to give them an idea what would be a further possibility in future to keep production there, still use the wood, but maybe make less pulp and paper, and maybe make more bioethanol. So this was really a key aspect, and we analyzed this also in the social assessment. And based out of that, we created the perspectives for the realization, and also what is still the research demand. Yeah, so what has to be researched, what has to be developed, that this really is um, going to happen. Um, the final results, I don't show you numbers, I just give you a brief orientation. In total, we have analyzed 12 different concepts of making bioethanol from wood. Yeah? Um, this is not surprising, because in many LCA studies, as you start to compare with something and you want to compare different processes, you soon end up with several systems that somehow seem to be of interest. So at least we have this 12 concept, and we put a value on state of technology, on the economy, and on the environment. And that there are smaller plants and bigger plants. Yeah, so the first ones are really small, because with the black liquor you can only make up to 5,000 tons bioethanol per year, because they have very less sugar in the black liquor. And this is at least uh, from an economy point of view a very small facility. And even the lignocellulosic, also Professor Singh mentioned that you need a certain scale, used economy of scale, due to efficiencies, but also to investment costs, and the investment is high, the capital cost is high, and also the feedstock is high. So these smaller plants, for them, it's quite tricky to be that small, and so therefore we added also here additional feedstock here beside the black liquor, also add cornstarch, and for only corn, to also have additional feedstock, to see if it then performs better. And you see the state of technology is existing, but the economy has many red signs, so to say. And for the environment, only in few cases at least, we see there might be a certain a certain gain. Our goal was that the greenhouse gases minimum must be reduced by 35%, and we want to reduce fossil energy by minimum 50%. This was a target we have discussed with the stakeholders, and saying all the system reaching that get a green one, and the others get a red one. If you go to the bigger facilities using black liquor and wood, the size of the plant is increasing. Yeah, so they make up to, in the biggest case, up to 100,000 tons bioethanol per year. This is at least a reasonable size. And here you see the economy looks more attractive, yeah, because it's bigger. But for the technology, we had to make many assumptions because you cannot yet buy these systems. Yeah? So there is still R&D demand. So the risk of building such a big facility from a technical point of view is really big. So still here is a big demand on state of technology, whereas here for the black liquor bioethanol production and from corn and sugar, that works. That works, but for wood, in that still has to be developed. But you see, the environment is green. So the greenhouse gas reduction of using wood to ethanol is quite well, and also the economy integrated in such a pulp mill at least looks relatively feasible, also from an economic point of view. So the result from this project was that the pulp and paper industry now have a perspective where to go in the next 5 years to come. And they also now are doing much research activities to further develop the technology, that the technology will be ready when they need it. Because they see if pulp and paper is going down, they see there is a need. So they have now created really a strong interest and doing much research on the overall process. I think this research is also focused on the sugar making, because this is a key process, but also then the further processes, and always the question of lignin, what to do with the lignin. To burn it is good for the energy, is good, it's renewable energy, but some guys say lignin should not be burned because you can also process it to many different products. But anyway, I'm coming now to another activities on the biofuel balance we do so far. This, as I mentioned already several times, this is the Renewable Energy Directive in Europe. And each liter of biofuel in Europe needs an LCA showing that the biofuel has a greenhouse gas reduction minimum today 65%. And the system installed is really from the farmer to the processing until the final consumption. And this is just a directive starting in 2009, where they introduced this LCA thinking, and it's not in the main text. In the annexes, as I already mentioned, is a formula. You don't understand the formula, but it's at least a little bit simplified LCA calculation by looking on the emissions from the cultivation, emissions from transporting and distribution, emissions from processing, emissions from the fuel in use. So at least all the relevant terms for the unit processes are here summarized, and it's a minimum 60%. From this year on, it's 65%, that the fossil emission should be reduced by 60%. And this has at least the main simplification in this methodology is, on one hand, they apply only energy allocation. Yeah, so it's only energy allocation, which in most of the cases give you lower greenhouse gas emissions than the substitution approach, but this is for simplification. And secondly, the emissions from the production and end of life phase is not included. Yeah, so at least it's not a real LCA, it's more a well to wheel consideration, because the well to wheel mainly considers the operation phase from agricultural production to the vehicle, but not including the production and the dismantling of the facilities. But as you've seen before, the vehicle production roughly makes 50 to 20% in the overall system. So at least these values are 50 to 20% better, compared to a total LCA. Yeah? The reason for that is they stop at the biofuel, so their functional unit is grams CO2 equivalent per megajoule fuel. So they stop at least at the fuel, and they say this directive is mainly relevant for all biofuel producers. Yeah? So they cannot change the vehicles, they have no influence on the vehicles, so their business is making biofuel. Therefore, this directive was developed for that. And when they started to develop this methodology, we had very much work, because all the different ethanol producers wanted to know their balance, because they were still discussing about the reduction targets. So we had many bioethanol facilities all over Europe, and we helped them to calculate their initial value. And we did this also for the Austrian bioethanol plant. We have only one. It's close to the river Danube. So here you see the river Danube is running here. It's a big industrial facility. I think you know how an ethanol facility looks like. They use more than 600,000 tons of maize and wheat mainly. They have also some additional feedstock, but it's mainly maize and or corn and wheat. And they roughly make nearly 200,000 tons of bioethanol, and also roughly the same amount, 200,000 tons of animal feed. And really, the value from the animal feed, from an Austrian perspective, is quite good, because we are really avoiding the import of animal feed from abroad. Yeah? So this is really also very strong motivation to not only have the bioethanol, to also have the animal feed. And in fermentation you produce pure CO2. So if you collect that and use it for any purposes, for technical application, but also here for beverages, they also started to collect the CO2. Yeah, and the collection of the CO2 is also part of this formula, because if you this term here, emission saving from carbon capture and replacement. So if you really collect the CO2, you also get a credit in that formula. Yeah, because on one hand you need additional energy to collect it and to compress it, but at least you get a credit because you're really also substituting fossil energy. And we calculated, at least we have only one bioethanol facility, and we calculated the greenhouse gas emissions in gram CO2 per megajoule, and you see the gasoline value is in the range of 90. So the value in the renewable energy is a little bit lower than the real Austrian value, but the green bars with the different feedstocks, you see they have significantly lower greenhouse gas emissions. If you even use this DNC starch slurry coming from a wheat starch biorefinery, this is even having nearly 90% greenhouse gas reduction, because it's a side stream from the wheat processing to different wheat products, and that is also used here. And the current feedstock, as I've mentioned, as it's very close to using corn and wheat, at least that the average value is a 25 gram CO2 per megajoule. And you also see this value is because we use the CO2 from the fermentation and can sell it. So this is also part of this regulation. If we don't do so, the value nearly doubles. Yeah, so collecting the CO2 and using the CO2 is a good thing for greenhouse gases, but it's also a good thing for the economics, because you have an additional product. And if you can make money out of that, that is the concept of biorefinery, to really use all the products you're creating to also make additional economic value. We did the same analysis also for the biodiesel producers in Austria. And biodiesel, you always have to compare to fossil diesel. The fossil diesel has a little bit lower greenhouse gas emission than the gasoline, a few grams less. This is due to the process in the oil refinery. And here again, you see these 6 or 7 different feedstocks we use in Austria to make biodiesel. We have at least very much waste cooking oil in the overall mix. But we also use very much rapeseed oil, sunflower oil, soy oil based in Europe. We also use animal fat, yeah, from slaughterhouses is used a little bit. So they have a good balance, because they are residues. So they have a low emission, because you don't have to cultivate them. And at least in the overall reduction, the biodiesel is higher than the bioethanol. It's in the range of 35 grams CO2 equivalent. So it has a reduction at this time of 60%. And we analyzed this in upfront before this directive came. So the biodiesel producers could easily agree to a first target of 35%. And they have also seen that they have the opportunity to go up to 80% stepwise in future. So this really increased the acceptance of this regulation, because the producers saw this is a way we can live, and this is a way to go forward. And of course, it really helps to reduce greenhouse gases. And the introduction of biofuels in Austria was the biggest activity in the last 15 years to reduce greenhouse gases. So if you see how much the biofuels introduction reduced the total emissions of Austria, that is the biggest measure taken in the last 15 years. So this at least was the target also to reduce greenhouse gases. Here a little bit a detail to highlight again how relevant it is to at least include also the N2O, especially for rapeseed. You see the rapeseed has significantly more N2O than the soy. The fossil diesel nearly has no N2O in the production phase. There's a little bit methane, but most of the fossil diesel is coming from the CO2. But for the biodiesel rape, it is nearly 50-50. And of course, the waste cooking oil also has no N2O, as it is a residue product and not directly affected by the agricultural N2O emission. Yeah, and based on this renewable energy directive, it is mandatory that each country in Europe makes an annual reporting about the biofuel. How much biofuel they produce, how much they import and export, what is the feedstock, and at least so every year there's a report coming out from our ministry telling exactly how much biofuels we're going to have. And this picture is a quite interesting picture. You see here, he is harvesting some grains, and these are photovoltaic panels in agriculture. So this here's a full agricultural photovoltaic. This is in the years to come now an idea to most efficiently use the ground. And this is just a pilot place in Austria where you really see you can combine different functionalities on the field. And this is also when you're calculating the area demand of biofuels. If you have also photovoltaic here, you need less land for cultivation. Even if you do a photovoltaics like this, they have animals running around, the chickens and the goats. They are used to have the grassland below. So it's also a double function of the same area. You make electricity on the panel as a roof, and below you have the chickens or the goats. So this is also something coming, because the more efficient you are able to use the land, of course, the better it is. And then we have really established a system to prove the sustainability. So there's really a system in place that starting with the farmer. So the farmer has to report certain data, mainly on yields and fertilizer use. He has to report in an electronic system. And so each ton of rapeseed or grain he's selling to a biofuel producer, he has to report some key data. So it's not hundreds of data, it's maybe 20 or so. I don't know the details, but that's all going in a system. And then the one who is transporting from the farmer to the bioethanol facility, he has also to report how many kilometers he did take, how much load he transported, because all this data is relevant. And then the biofuel producer also has to report, currently on a monthly basis, to report how much energy they needed, how much bioethanol they produced. And at least this is all done electronically. So finally, you know for each liter of bioethanol, you know exactly which feedstock has been used. And even if that sounds maybe like much work, finally, the main idea is really to make sure that all the biofuels used in Austria or in Europe really fulfill all sustainability criteria. Because sustainability is the key priority, and only using biomass is not a guarantee that it's sustainable. You really need to fulfill certain criteria, and this is at least a good system being established already since nearly 15 years so far. And I personally would like to have such a system for all products. I told you about the automotive industry. They also are going more and more in that because they also have to report quite soon about the carbon footprint of making their vehicles. Yeah, but you can also do it for each product coming from agriculture, but also for each laptop and each mobile phone. And so, in my thinking, of course, I'm quite sure it will come. The question is when it will come, but I'm quite sure this system will come. And there are also limits will be set. If you are above a certain amount of greenhouse gases for a laptop, for example, maybe you're not allowed to sell it on the market because, and you also have to say it must decrease, and you have to prove that you decrease it. Maybe you have also seen, I've shown you the liter of milk where you find that. I bought a sport shoe recently, and also in the sport shoe they told me it's a 10 kilogram CO2 by making this sport shoe. So more and more companies also reporting currently voluntarily about their greenhouse gas emissions. So LCA is really a part of our daily life, and it will even become a more relevant part. So we need many LCA experts, yeah, to do all this work recently on a good way. And so at least this is the proof of sustainability. Yeah. And here's just some key facts if you're interested that how much Austria is using on biofuels. I don't want to go through the details numbers, but it's at least biodiesel and bioethanol being used as a blending. Yeah, so we have the B7 as diesel and the E10 for gasoline, where we can use it. We have only ETBE is a very small fraction. Also the HVO is very less, and the biomethane is nearly invisible. But anyway, it's the right way. The interesting thing is if you look on this reporting of Austria, in Austria we use very much waste cooking oil for making the biodiesel, and this has a very good greenhouse gas balance, as we've seen. Yeah, and you get a better price if you have lower greenhouse gas emissions. Yeah, and so most of the biodiesel produced in Austria from waste cooking oil is exported mainly to Germany, because in Germany the price level in general is higher, and they pay more for a biodiesel with low greenhouse gases. So the curious thing is, on one hand, Austria is exporting biodiesel, but as we need biodiesel also in our country to fulfill the requirement, we're importing biodiesel, yeah, with a lower greenhouse gas saving, I assume also a lower price. Yeah, so this is also part of the economics. Yeah, that you produce it and you export it, and the same product you're importing for any reason. And this is really happening in Austria, because Austria was a front runner in collecting waste cooking oil. And I think this is a really good way to start with biodiesel to collect at least the waste cooking oil. So at least you see here, roughly you can say if I'm substituting 1% gasoline or diesel, you reduce the greenhouse gas emission by 60% in average. So it's not 100% climate neutral, but it's at least on the right track. Okay. The take-home message here is, what do you need? You need a clear description of the biofuel production is necessary. You need an energy and mass balance. Consider the co-products is essential. The main focus is always on greenhouse gases and primary energy, as we can judge them in LCA quite well. Yeah, this is important. Biofuels have lower greenhouse gases, but still further reduction is necessary because the things are going on. NGO is always visible in these agricultural-based biofuels because the NGO is so relevant. So at least advanced biofuels made from lignocellulosic become more and more technically and economically feasible. They promise to have a reasonable greenhouse gas balance. Austria is having roughly 10% renewable energy in the transportation sector, but you also count for the electricity used for trams and trains and so on. That's also in the package. So roughly 7% of them are a biofuel. So the biggest share of renewable energy in Austria is in the transportation sector is biofuel. And last but very important is really to guarantee the sustainability, to really show that uh, the systems are sustainable from the very beginning. Clear targets are set, a clear system, clear electronic way to guarantee this overall certification project, to make sure that each liter of biofuel really has a significant greenhouse gas reduction. Yeah, that was it so far from my side. Do you have any questions?
Hello. I just wanted to clarify something in one of your slides regarding 12 concepts of sustainability. There plus minus and in brackets you are keeping minus minus plus minus. Some it was not clear to me actually. What do you mean by that?
I show it
Yeah,
to you.
please.
Yeah.
Yeah.
The
Sure.
scale here is relatively simple. A green plus means the technology is existing and state of the art. Yeah. And the red means it's not good, and the brackets was based on the sensitivity analysis. Yeah. We change the parameters and see if in a changed technical setup, maybe this system becomes economically feasible. And here, for example, you see under specific conditions, you're on the green side. So this is the brackets is a part of the sensitivity analysis, which is very relevant. And you see, you can do it economically, environmentally friendly under certain conditions. But you see, it's very hard because you have two red ones. Okay. This is just to get a feeling. You have the average is plus, but if you're not careful, you end up with a minus.
Okay.
So it's really for high aggregated assessment.
Okay.
But it was easy to communicate that to the stakeholders.
Okay. So another thing is you also mentioned the biofuel production from lignocellulose is currently mostly from paper and pulp industry, right?
Yeah, this is state of the art. Yeah.
Okay.
So not all pulp mills have sugar in their pulp,
Okay.
but this is state of the art. And in Europe, I would say that only a few plants doing so. But the total amount is very less sugar in it, so the total amount of ethanol is quite limited. This is state of the art, but all the other from straw and wood, main focus is at least in Europe on straw more than on wood. I would say only the northern countries, Norway, Sweden, Finland, they have much wood, but generally the big countries, Spain, France, Germany, Poland, they have much straw. So a bigger focus is on straw.
Yeah. Okay. Okay. Thank you.
You're welcome. So the rest was clear. Very good. Do you have any questions on your homework? Or was it clear? Okay. So we make a brief break and then continue. I don't know what's the schedule, but a 10 minutes break or so, and then we continue with the last. That does not mean that they are wrong. They're just telling you they may be already 15 or 20 years old, and so you don't know how appropriate they are really for the current situation or not. So this is really a very sensitive area, and the more you experience in LCA, the easier it is to check if the orders of magnitudes are okay. But for a newcomer, it's really difficult, yeah, to handle that. And at least the more you step into this databases on the beginning, I'm honest, you're a little bit confused, yeah, because it's really tremendously what is in there, and at least you have to track back. And if you look, for example, only for one chemical, and you find in the list the same chemical 20 times, yeah, because it can be made from different sources in the database. Could be for Europe, could be for India, could be a specific process. So it's a kind of learning, and this is why this iterative process in LCA is so relevant. You end up with a first result and have to check what is a key contribution, and then go back and see if the key contribution is really appropriate. So as I've mentioned before, there are many different LCA tools that exists. LCA is a methodology, and normally in this tool, the methodology is properly included. In many cases, you start an LCA with a pen and a paper. Yeah? Especially when I'm in an industry, in a pulp and paper mill, we still very often see a flow chart of the facility, and then we start really putting the main unit processes on a piece of paper to start to understand the key processes. So there are many tools available. Some of them are open source. Most of them are really for purchase. And also many data sets are available. A few of them are open source. Most of them are for purchase. Our experience is all these tools, they calculate properly, but it really depends on the user. He has to know what he does, which is the same with all computer programs. Yeah? And at least the more sophisticated, these tools sometimes are very sophisticated. That means they have many things in there you don't really need at the moment. Yeah? And that sometimes makes it very difficult to see what do I need for my LCA now and what is meant for any other users. Yeah? And this is really very, very challenging. But that is a reason why I try to recommend at least two tools. They have the big advantage that they are based on Excel. Yeah, and Excel, I'm sure you all have opened once an Excel file and done a calculation in Excel. And when you do so, one of these models is this GREED model. The GREED model was developed in the US, I would say 25 years ago, and it has globally more than 60,000 users already. So it's really a widespread tool with many, many users. And the good thing on that tool is it's for free. Yeah, so you can download the packages, and you get also there are tutorials to watch and see how the grid is working. It's very spread in the academic sector. Yeah, so half of the users are really academic. Yeah, so it really has a good functionality, and it has all data you need to run the model are already in the tool. This is all very great. They reflect to a high degree the US North American situation. But anyway, some of their chains are also happening in other countries. For example, battery production or the mining of specific minerals. So at least all these data are really implemented in the GREED model. And the GREED model really is a full LCA covering, on one hand, when we talk about vehicles, the well to pump. So really starting from nature to develop the fuel supply, and also in a vertical way the building of the facilities here on the example of building the vehicles. The model is split in several parts which are directly connected. So at least it's a quite good life cycle analysis model, and they update it year by year. So now you get a brand new version that was published last week. Yeah, so really a good update on data, and how does it work? Just to give you an example, the colleagues from Argonne National Lab, they used to take this process about the flubber production. And flubber is not a real product; it's a fictional product. Just to explain how you do it. So if you want to insert a new process, you make the flubber process, yeah, and you have specific inputs, you have specific emissions, and you put in flubber ore, and the final thing is the flubber. And you have to think about where is the material coming from I need for for making the adamantium, yeah, I also have to insert a new unit process. So it just guides you through how you build up a new process. And then you have the flubber ore, then you add a process. The black ones are all unit processes where you say, I need the ore mining first, and to insert that. Some of the materials are already in the database. If you need a new material, you have to start a new data set. But I think, or I assume that of the most of the data you might need for one of your first or initial LCA, I'm quite sure you will find all these data in the grid model. In different units, you can also change the different units from liters to kilogram and the heating value and so on. So this is works relatively um, relatively well. And at least what they do, they give you a background data for the baseline technologies. Yeah, so you will find in for transportation, ships, trucks, aeroplanes, if you want. So for the baseline technologies, for power plants, for heating plants, they are all there. Yeah. Secondly, also for field operation, um, and the farming data, and also extracting oil and ethanol plants. That is at least very well uh, integrated there. And still, you always have to be careful about the data you really use for your calculation. Yeah? And in the beginning, of course, if you have a supervisor helping you with that is quite well, because when you end up with a result, you need a clue if this result is somehow reasonable, or is it not. Yeah. But anyway, I should this this grid model is I think a very good thing. It includes many different vehicle technologies. So all the vehicles, and if you deal with biofuel transportation fuels, of course, if you also include the vehicle, is very nice, because then you can really compare it to different fuels, especially when you compare a bioethanol vehicle to an electric car. You always have to go on the car level, because per megajoule of ethanol or megajoule of electricity, you cannot make a reasonable comparison how much you emit when you drive 1 kilometer. And they really have many different technology, uh, conventional combustion engines, but also hybrid electric vehicles, fuel cell vehicles, battery powered vehicles, plug-in hybrid. So everything is at least available, and to use these data is a perfect starting point. And even if you don't like this data, you can copy them and insert your own data. If you think, oh no, my vehicle is a little bit heavier or less heavy. So this is really a good thing. The other good thing is that this grid model really covers, I would say, all energy systems from today and even from future. You see here, for example, they have a very big block on renewable energy and fuels. Yeah, they're also covering hydrogen, electricity, but this one is really covering different first generation feedstocks, corn, sorghum, soybeans, and so on, and also second generation feedstocks. And they also have algae systems in there. So for your need, this is very well developed and accessible for the biofuel area. And you find many default values you can use. Yeah? And if you have a different pre-treatment step, you take the existing one and you modify it maybe to your needs. So it's relatively easy to include that. So they really have a big amount of different energy carriers, and that is relevant. And you see that this is a similar picture of making electricity, because electricity can be made from so many sources, and electricity is always a key in LCA. Yeah, it's always a question, where is the electricity coming from? So in that model, you really have the possibility. You have all the different ways of producing electricity. And if you only want coal power plant or only renewables, you can put in your own share where the electricity is coming from. So, example, you can insert the Indian electricity mix, and you get an emission factor for the average Indian electricity. And this is at least very good. It additionally really has a full LCA, so you get also for all the power plants, you get a list of materials you need to construct a power plant. Yeah, so you really have an idea how much concrete, how much steel is already in there. And then you can also push a button and then you get the results, how much CO2 is emitted when you build this facility. Yeah, so it's really a very, very comfortable tool. And it has also a separate tool which is integrated in the other, specifically dedicated to land use and land use change. So if you want to step into the area of land use and land use change, I really recommend you to have a deep look on this, because it's on one hand explains, and on the other hand it gives you the key factors and many data, and they always refer to the data. Yeah, so from a scientific point of view, it's really well done. So maybe the data are 2 or 3 years old or even older, that does not matter. Still, it's the best available scientifically sounding data set that can be used for analysis like that. And it's also with the land use and the land use change. Recently, in the discussion on these electric vehicles and the battery production, there was a long discussion, how do you really make a battery and where's the raw material coming from? And in the GREED model, they spent much effort. They really visited the ore mines in China or in South America to really see how they're producing the materials, the specific materials, especially the lithium and the cobalt, and yeah, however, and how you really produce a battery. So they have really the most recent data in this area on battery, and also the other data. Um, so you see from my enthusiastic description, at least this is really a very recommendable program, really covering a broad range of different things. And still, you need to know what you do. Yeah. So really, still, you need to know what you do when you handle such a tool. You really have to be careful. Then the good thing is you can use this tool as they're already predefined chains. Yeah, you can start looking on the existing chains, look on the results, and see how they look like. Yeah, and you look on the bioethanol car, and then you go in the different processes and see what is in there. That's a way to get to know and learn on the program, and then you can start in changing a number and see how much it affects the result. And this is at least one way to get to know the program. Um, in the past, at Yoneum, to be honest, we always checking different tools. And as I mentioned before, none of them is fulfilling all our needs. So at least we're using a mixture of different tools and databases. And sooner or later, we always import or export something from Excel. Yeah? Because this is at least the most common data format where most of us are familiar. So at least sooner or later, we really only can use programs that have an interface to the Excel in both direction. Then at Yoneum, it is reasonable. And you see here the prices. If you pay 3,000 euros per year or even more, I think that's not cheap, even for universities. I don't know what is the price for universities, but some of these softwares are really expensive. So you should consider that. The only one is this free one, this Open LCA. This means open really because this is freely available. But with the tool alone, you cannot work. You still have to buy a database, because in Open LCA normally there are no datas included. So you still need to find the data. I don't want to go through the different models. The only thing beside the GREED model, this Open LCA model is freely available and is relatively good. The Echo Invent database is very common in Europe, yeah, because it was developed in Switzerland. They have many data sets. it's not for free. And the good thing on the EcoInvent is that you find all the different impact categories, as Professor Singh showed us with his midterm and endpoint indicators. They are all in the EcoInvent. Yeah, so they really have covered all the impacts, whereas the GREED model is relatively limited in the impact. So they are considering mainly inventory data about the primary energy consumption, the fossil energy use, the greenhouse gas emissions. They have air pollutants in there, the SO2, the NOx, the particles, and the water consumption. So they only have these five, where all of them, except greenhouse gas emissions, at least they're all happening on the inventory level. Only for greenhouse gases, they do the assessment by taking the CO2 equivalent of the different gases and calculate the CO2 equivalent. Because they believe, that's the American belief, they say the inventory data we like more because they are really on a physical basis and they already help you to compare and judge on different systems. This is at least their philosophy or their strategy, to keep as long as possible close to the inventory data. That's why the GREED model has at least a limited amount of impact categories, but I would say still a reasonable amount, and for a starting point, the best. If you really want to go further, you have to go to EcoInvent, I would say, because I think EcoInvent is at least the, the only database. They have really all these indicators, but as you open, for example, the sheet on human toxicity, and you get a long list of different assessment methods of human toxicity, this is a challenge still. Yeah? And so what is the take-home message from this? There are several LCA tools and databases are available. They calculate properly. Yeah, so if you handle them properly, yeah, so if you do the right thing in the program, it works. And the key questions for you is really what is needed. What do you need? What is your question? And secondly, also this transparency. Yeah? How transparent are these calculations? How easily do you find the key data, the basic data, the emission factors? And how easy is it to integrate new data in the model and to also get out the results for any further use? That's also relevant. I forgot to mention that, for example, for the EcoInvent database, where you have to pay for, you are not allowed to share the emission factors with somebody else. So if you publish a research paper and you took the grid electricity mix from Austria from the EcoInvent database, you're not allowed to put in the 200 grams per kilowatt hour taken from the database, because this is not allowed. Yeah, you can only show intermediate and final results, so things you calculated. And this is a big disadvantage in transparency. Yeah? Because if I review a paper and he tells me I use the Austrian electricity mix, okay, but I also want to see the gram per kilowatt hour he used, yeah? Because then I know if this is reasonable or not. If he tells me 2000 or 20, I say this is not wrong. So in terms of transparency, this key data, yeah, if you drive an electric vehicle and they only tell you I use the Austrian electricity mix and it's 3 times better than the gasoline car, I don't believe this until I have seen exactly what electricity mix he has assumed and what is the CO2 value. Yeah. So this is at least also things you have to consider, and in the scientific community, at least it's necessary to put the key data also in, at least in an annex or wherever of your paper, because transparency, as scientists, transparency is always key. Yeah? And if that is not possible because of the copyright of this product, so this is sometimes also for us difficult if we use data from EcoInvent to not harsh the copyrights. Okay. The last example is at least focusing on one tool which has been developed in Europe, which is only dedicated for biofuels. Yeah? So it's this BioGrace tool. You can download this tool for free in the internet. It will give you a message on the very beginning that this tool is not reflecting the current regulation in Europe, because the tool was not updated for a few years while the regulation changed. But this does not harm the calculation in the tool itself. So this bioGrace tool is only dedicated for biofuels. And they have in the most relevant biofuels, and you can also use data that are already implemented there. And I think this is maybe the easiest way to jump into LCA of bioethanol, for example. And in this bioGrace tool, again you see the key processes starting with agricultural land. So in the tool you find one sheet about cultivation, about transport, the bioethanol plant, the distribution of the bioethanol, and the vehicle if relevant. I think this tool stops at the biofuel, so it ends after the bioethanol, giving you a value in megajoule, gram CO2 equivalent per megajoule. And at least I have just to guide you quickly through the system. And this is an example from bioethanol from sugar beet. And this is the summary table. We are telling you that the final result of producing ethanol with this data we use here, you end up with 40 grams CO2 per megajoule. And it also tells you here, is that allocation necessary for the process or not? So you also see on one glance the allocation factor. It's also nice, it also shows you the unallocated value. So you have a clue if you exclude somehow the byproduct, how much higher would be the emission if you put everything on the shoulder of the bioethanol. And it also gives you, shows you in which step you have the highest emission. And again, you see it's the cultivation and the processing which adds you up the most. And so this tool starts with this summary, and then you go step by step. The different cultivation step is the first one, and it's at least relatively the white cells here. They tell you first about the yield. What is the yield of the sugar beet, and what is the water content of the sugar beet? Yeah, when you harvest it, that's something you have to know. At least also how much diesel do you need for the machineries. If you don't have your own value, use this value. Yeah. So here are already default values in there. If you don't like that because you have your own calculation, talking to a farmer how much liter diesel he needs, then you can put in your value. If that is not the case, you can use the diesel consumption for all the machinery, yeah, for the seeding, for the harvesting, field preparation. And then here you have a long list of the agrochemicals, we call it, which are mainly the fertilizers. It's a nitrogen fertilizer. It's also a manure. You can also fertilize with manure. With a calcium, kalium, phosphor, even pesticides. Yeah. There are at least how many kilograms on pesticides, on fertilizer you put on the field. Yeah. And if you have your own value, if you don't need 120 kilogram nitrogen, you only need 110. You can override that. Here, finally, also the seeds, yeah, because making the seeds also, when you start sowing, you need seeds. Also, the making of the seeds is an emission, and also how many seeds you need per hectare. So we need a 6 kilogram of seeds. Yeah, the farmer knows that to plant 1 hectare on sugar beet, and finally also the N2O emissions. Yeah, so how much N2O is emitted? Here it's a 3 kilogram per hectare and year. The program itself, oh, I think I have not printed it out, but the program itself has also an extra sheet where you can compare different N2O emissions. Yeah, so at least also here it's a default value. If you don't have a better one, you just insert here. They used also the N2O emissions, for example, from the IPCC. Yeah, so they also are on the safe side. Or there is a separate sheet saying you can calculate your own N2O, where they have a modeling of this relatively complex methanol, not methanol, N2O formation processes. If you use wheat cultivation, it's the same sheet, but of course wheat you grow differently. You have a different yield, you have a different moisture content, different inputs, but the same is also available for wheat. And again, if you have your own data, you can always insert it, so you have a relatively good way. So these are the key data for cultivation, yeah, which is clear. The farmer needs diesel to run the engines. He has a yield, that's what he harvests, and he has to put things on the field that something is growing, which is fertilizer and plant protective agent to do that. And then the next step is you have to transport the sugar beet to the factory, and the transport is mainly a question of the kilometers, yeah, how many kilometers you transport it. There are different vehicles integrated there, a big one, a small one, and it also asking if it's running on diesel or any other fuel. But at least the transportation is relatively simple. But for transportation, the most tricky thing for transportation is you go to the field, take the sugar beet, and bring it to the bioethanol plant, and then you go back. But you, in most of the cases, you go empty back, yeah, because you don't bring something from the ethanol factory back to the field. For the sugar beet, sometimes they bring the earth, because when you harvest the sugar beets, they are cleaned in the sugar factory, and the earth is brought back. But normally, it's going back empty, yeah. And that's a question: if these 30 kilometers include both distances or only one. And at least you have to make sure that it's the full distance. Even the truck needs a little bit less energy if it's empty, that's for sure. That can be calculated in the kilometers, but normally it's the double distance for many products, not for all of them, but for many products. They go empty back, or they have a certain system, and in average it's they only run at 40% empty. But this is for transportation very important to really consider both directions, the empty and the full one. Otherwise, you're missing a certain fraction of the emission. So this has to be considered. And this is already the next one. This is the ethanol plant already. Yeah? So the ethanol plant also needs only a few inputs. Yeah. For example, the yield. So how much ethanol do you produce per input? So per megajoule or per ton of sugar beet going in the factory, how much ethanol do you produce? And how much sugar beet pulp, so this is the animal feed, do you produce? Yeah, so how much main product, how much byproduct, so this is included here. And then they ask you how much electricity do you need, and where is this electricity coming from? Yeah, and that has to be specified here, how much energy you need, electricity you need, and where is it coming from. And you also need much heat, so this part here is covering the heat. You also have to tell where you get the heat from for the distillation and all the facilities. So these are the key elements. All the other chemicals are not considered here, because in the final they need some additional chemicals, but their contribution to greenhouse gases is so small that in this calculation it does not change the result at all. Yeah? So from that point of view, it's really a good starting point, because it's relatively simple. You need electricity, you need heat, and you have to input the amounts of ethanol and animal feed you are creating. The same sheet for wheat, it at least looks the same. You input the yield, and you put in. If you have, in some cases, you have a CHP plant, a combined heat and power plant, yeah, where you use, for example, natural gas to make electricity and heat, which is a little bit more tricky compared to only use natural gas for heat and taking grid electricity. But this program also enables you to integrate a CHP plant, yeah, because if the ethanol factory is having a CHP plant, you are able to also insert this in this calculation tool. Yeah, and then at least we have the ethanol distribution And again, the distribution of the ethanol is at least a transportation process. Yeah? In that case, they say you're driving 150 kilometers. Sometimes there's a depot or a bunker where you collect first the ethanol and then pump it out. That's why they have a little bit of electricity of pumping in for storage and pumping out. And then finally, so it's a storage, and finally you go to the filling station saying, okay, the filling station also needs some electricity for the pumping, and then the LCA stops. So then you really have the value on greenhouse gas emissions per megajoule bioethanol at the consumer side, when you start filling in. So this is the system boundary of this system, and at least I would say this is the, if you're interested to start an LCA, I think this would be the easiest way to start doing it. And here you see again the differences, and all the data are in there. So it's fully autonomous, and you also find in the different sheets the values that are used. For example, the production of 1 ton of nitrogen fertilizer, it tells you how many tons of greenhouse gases you have, or it tells you about the diesel, how much greenhouse gases. So the key data are all in there. So at least it has a reasonable size, only focusing on biofuels, and it's a good starting point. And anyway, you can always change later if you like. Yeah, so it's really flexible on that. And I just have a screenshot. This is the database. It's an Excel table where you find all the necessary background data, the fertilizer and the diesel, it gives you the greenhouse gas emissions and the energy consumption and so on. That is all included here in a relatively transparent form. And finally, I show you the summary of bioethanol from wheat. Again, you have always a good summary, which is in LCA really necessary. You've seen with my fact sheets and so on, to really summarize the key things that are relevant to understand and interpret and communicate your results. If you can summarize them in a table, and that's very good. And you really see here the different contributions. And you see in that case, the bioethanol is having 26 grams of greenhouse gas emissions per megajoule. Yeah, so this is at least one of my nearly last slides. I have 2 more slides, but at least only summarizing up. We've seen that picture on the very beginning. Sustainability is more than life cycle assessment. Yeah, so we were mainly talking about the environmental part, but of course we all know economy and society are really relevant. But to judge on them, on all these 3, we think it's at least state of the knowledge. You need an LCA. You always need to consider the whole life cycle. This is the methodology to really judge on the environmental effects. And we at Ioneum, we are not only judging on the environment. I have also colleagues that use the same system boundaries, the same unit processes, the same definition of functional units, but they count in economic terms. Yeah, so then it's a money LCA, so to say. It's an economic LCA, and also the social LCA. Yeah, to describe the society is even more complex than describing the environmental aspect. But social life cycle assessment is also something coming up, and at my institute we're really doing. We have different experts in the different fields, but the system boundaries, yeah, and that's also the homework you have to do and present more tomorrow. The system boundaries are the same for the economics and the society also. Yeah, so at least it's always covering the whole, and at least some of these indicators you can already well quantify. Others are under development, but I'm sure in future more and more indicators will come up, especially also in the social area. I think that is also quite interesting, but still then you even create more indicators and even makes the discussion more complex. But still, this is something we have to deal with, because life is not so easy. There are so many different views, and the more scientific based information you have, it's a good starting point to discuss and talk to others and make reasonable decisions. For this one, I have made no take-home message. I was tired on the very end, so I made no take-home message. But thank you very much. And if you have any questions, let me know.
Hello. Thank you very much for the different databases tools which are useful for this biofuel related, sir. I have a couple of questions. Okay. Number one is I'm curious that which tool or which database you have been using in your last 20 years, which you prefer. That is the first question.
One good thing is that I do LCA since nearly 30 years.
30. Okay.
So we have many data gathered in-house.
Okay.
Because we have worked with the electricity companies, and so we have a certain data set we use in many of our research projects. We just say research internal data. That is one thing, and then we mainly use in specific projects the eco invent. In most of the cases, when there are very specific chemicals we don't have, there are so many chemicals, then we take them. Or very seldom, if we really need more impact than greenhouse gases, primary energy and land use, human toxicity. I think we never calculated human toxicity, but if we need more, we take the eco invent. And third, from the GREED model, this American model, we always like to look on that because it's so transparent and so easy to find the data you're looking for. So one is in-house, but for you, I would really recommend to use the GREED data, because they give you on the key impact, greenhouse gases, energy, a very good starting point. Very good starting point. And this eco invent is very big, very expensive, and very sophisticated. So for advanced LCAS experts, it's good. But if you want a starting point, I would really say that the GREED model, or you can also from this biograce model extract some key data for fertilizer production and so on. I really recommend to use these. They're transparent and the orders of magnitudes are perfect there.
Okay. So when we use this biograce sheet, what kind of errors we may get? Like some common errors. Like do we need to fill all the details? Otherwise it don't run. Like how it suppose.
No.
So you may not have some data. Of course, we need to have everything if you want to do proper LC analysis. But let's say some data set is missing. One of the box we don't have. Whether it will run the program and give you the results or
when you download biograce, even the GREED, if you download it, it runs because all the data are in for the defined chains.
Okay.
So it works.
Okay.
If you delete one, it still works, but then it's missing some input. But when you download it, everything works perfect. You can calculate everything. So with the predefined cases, it works perfect. And if you make something wrong, you take the original version and start again. So it really works perfect. So it's really a step by step. You can start changing something, and then you start defining your own processes. So really you can learn step by step and compare it to the existing ones. So it's really fully functional and everything is in there to run it.
Okay. Thank you.
Hello, sir. Sir, I am about to ask that, like we have some standard values to put in the software for the LC analysis, and you said that yesterday Volvo company released their CO2 analysis, and their values were much higher than what LCAU did. So, from where did that difference came in the LC analysis?
That's a good question. On one hand, Volvo also uses in certain parts eco-invent data. And the difference mainly came from that we have underestimated the effort and the energy input you need to make a vehicle, yeah, because a vehicle consists of so many parts, yeah, and Volvo knows much more of making the different parts of a vehicle than we did, yeah, or in literature you found, and we had so far. So this was at least the main difference. And secondly, one difference was in the battery making, because depending on who is making the battery, we took an average, global average value, which is an average from many battery producers. But Volvo has a specific supplier of the batteries. I don't know where it's located, and they really got data for their specific batteries from their supplier, and there might be a difference. And secondly, or thirdly, 1 ton of steel is 1 ton of steel. But there are so different types of steel and characteristics of steel, but also where you make the steel. And we, in our generic data set, said we use data as a global generic value, so a global average value. Yeah, but Volvo buys the steel at a certain supplier, yeah, and they also got the value from this specific supplier. And steel making here in India is different from Austria and China or wherever. So at least they had more information, specific information related to the product. You never get as a scientist because they don't tell you where they buy the different things. So this was one reason they have more specific knowledge where the battery is coming from, where the steel is coming from, and how much energy they really need to build the parts of the vehicle and to assemble them. Yeah, and this were the main reason why we have underestimated the results. And this is at least part of the game because LCA is always improving. Yeah, this is an iterative process. If you publish a paper today, this is state of the art. If you do another year of research, you iterate and you come to a new result. And this is at least the nice thing on LCA. It progresses, and the more transparent the documentations are, which data they use, and to also identify where we have different data. Yeah, and not saying, I say the best data is the one you really put transparent in the table, more or less. Yeah, this is the best data. If people start to hide data, that yeah. So the best way is really to put your data on the table, yeah, and then discuss about the table, about the figure. Okay.
And I think that's all for today. And tomorrow we'll be having exercise. So come prepared with your PowerPoint presentation on the aspects which have been given to you. Make use of the slides I have shared with you, everything, and some of the software which he has discussed. Some of them are open source software, so you can make use of those software also. So thank you, and we'll meet tomorrow.